Consider the rational function y equals x cubed minus 13x minus 12 over x minus 3. What we're looking at is the end behavior of rational functions, just looking at the end behavior, assuming we know what to do in between the ends. Okay, find the zeros, find the intercepts, find the asymptotes. Okay, we're not dealing with that part, just the end behavior. So the end behavior, excuse me, of this function it turns out to be dominated just by the x cubed in the numerator and the x in the denominator, because if x is big, only the x cubed in the numerator really makes much difference. Like if x is 1,000, then x cubed is 1,000,000, whereas negative 13x, when x is 1,000, x cubed is 1,000,000,000, not just 1,000,000, 1,000,000,000, whereas 13x is just 13,000. Okay, this is much, much bigger than this, and 13,000 or even 13,012 compared to 1,000,000,000 is insignificant by most, for most purposes. It's very insignificant. Okay, and for the denominator, if x is say 1,000, then 1,000 versus 997, 1,000 minus 3. There's not much difference. So for large x, the only terms that really matter are the x cubed and the x, and we can pretty much just forget about the other terms. So large x, y is pretty much just x cubed over x. Now say that's sufficient to determine what's going to happen. Okay? Now, of course, x cubed over x is x squared, which means that at some point this function is going to start acting like just plain old y equals x squared. So at some point this function is going to take over, and whatever happens in between is going to become insignificant. Now, what happens in between is that this function has zeros, as we can find if we factor at negative 3, 1, and 4. And the denominator, of course, has a 0 at x equals 3. So we're going to have an asymptote at x equals 3. We're going to have zeros here. The end behavior is just what we've indicated here. For large positive and large negative x, the function goes up just like a y equals x squared parabola, but in between it's got to go through these zeros, and it's got to have this asymptote, which is going to give it a graph that looks maybe something like this, and then maybe something like this, where it approaches the y equals x squared graph as an asymptote. Another way of looking just at the end behavior, not how it articulates with the rest of the graph, is if x is a really big positive number, then this is clearly a really big positive number, and this is a really big positive number. Dividing a really big positive number by a big positive number is going to give you still a big positive number. If x is a really big negative number, then this is negative, and when you divide, this is going to be bigger than this one, and the result is going to be a negative divided by negative, still going to be a big, and it's going to be negative divided by negative or positive, consistent with the idea that y equals x cubed over x is pretty much all you have if x is really large. Again, the rest of the terms, the negative 13x, negative 12, and the negative 3 kind of fade into insignificance when x gets really big. Now let's consider this function. We have an x cubed in lower terms here, x squared in lower powers here. So the top is a polynomial of degree 3, the bottom a polynomial of degree 2. If x is a very large positive number, again, only the x cubed and the x squared matter. And of course, that's just x. And I'll say that's sufficient the same way it was previously, which means that the graph of this function will, in the first place, if x is a large positive number, then you're going to go to a large positive. If x is a large negative, you're going to get a large negative. And you can analyze that here too. If x is a large positive, then this is an extremely large positive. This is a very large positive, but this is a bigger one than this, so that when you divide, you get a large positive number. If x is a large negative number, well, this one's negative, this one's positive. You're going to get a large negative. See, end behavior is as indicated, but just knowing that near the ends, y acts like x, we see that if this is the line y equals x, whatever happens for smaller values of x, the graph is going to have to approach y equals x as an oblique asymptote as x goes to infinity, as x becomes a large positive number, and as x becomes a large negative number. Now it turns out that this function has a couple of zeros in the denominator that give you vertical asymptotes. Those will actually occur at 1 and 4. And note also, I changed this 1 to a plus 1. I'd written it minus 1 before. But in order to have the asymptotes at whole numbers, my intention was to have a plus 1 there. So we have vertical asymptotes at x equals 1 and 4. That's going to be here and over here. And then we have zeros at the zeros of this function, which we have seen previously down here. So we're going to have behavior in between that acts a lot like this. Of course, the end behavior is a little different, but the graph is going to go through all these gyrations. It's got to go through these zeros. It's got to have these asymptotes. But when it gets past that point on the right or on the left, it's going to start approaching the y equals x and the y equals negative x. It's going to approach it rather quickly. So I'm not going to draw the graph because I want to focus on the end behavior. But the end behavior is that the graph is going to become asymptotic to this line, to this horizontal line. As a final example, y equals x cubed minus 13x minus 12, the same function we've been looking at, over x to the fourth plus 5x squared minus 3. For large x, this acts like what? You should be able to tell me. You should be able to pause and think this through before I write it, but here it is. Acts like 1 over x. And we can also say, well, if x is really a large positive number, x cubed is a really, really large positive number, but x to the fourth is an even bigger one, so that when we divide this by this, we get a really small result. Or if x is a large negative number, we again get a really small result, although if x is a large negative number, this is negative and this is positive, so we're going to get a really small negative result. So we can say that for large x, this acts like y equals 1 over x. What does y equals 1 over x act like? Well, we know what the graph of that looks like, or we definitely should know it by now. Looks like this and like this. Now, for the asymptotic behavior, that means that the graph is going to approach 0 as x moves out along the positive x-axis or the negative x-axis. However, it's not going to necessarily act like the graph of 1 over x in between. For example, this thing again has zeros where it has zeros. Those zeros are going to be at -3, 1, and 4. And the denominator is going to have some zeros as well. See if you can figure out where this denominator is going to have zeros. I'm going to pause and be back in just a second, so you should pause and figure out where the zeros of this denominator will be. Okay, if you use the quadratic formula to set the denominator equal to 0, you'll find it has zeros around -5.5 and +1/2. So you're going to have vertical asymptotes here and here. The function is less than 0 to the left of x equals -3, so that the graph is going to have to turn like so. And then it's going to come up from this negative asymptote here, and it's going to have to go through the y-axis at some point, and then it's going to go off to positive asymptote. Then it's going to come down from that positive asymptote, go through this 0, come up through this 0, turn around, and then it'll approach this asymptote here. Okay, so we can erase this much of the 1 over x graph, but this graph will join up with the 1 over x graph, and that won't actually join up with it. It'll become really, really close to the 1 over x graph after we get about here and over on this side of the axis. So, 1 over x is positive and near 0 for large positive x, negative and near 0 for large negative x.